Mrs. Hingham, are you there?
Driving, sir.
You're driving? Okay, so I'll go first then. That's fine?
Yes, sir.
All right, good. All right, good afternoon, students. Mrs. Hingham, it's her turn to get caught in traffic. So she is on her way home. So I'm going to start and then she will join at some other time. So Miss, please be safe as you go. And we pray that God grants you your safe passage. All right. Where two or three are gathered, there he is in the midst to bless. And indeed, we are going to be expecting a blessing today. Nothing less but a blessing. So let us just, in the true Mrs. Henningham style, I say, gentle Jesus, she says, the early morning prayer, let us go with the prayer. Let us pray. Father, we thank you for this day. We thank you for who you are and whose we are in you. We thank you, Lord, that you've granted us the gift of life. Father, we pray that at the end of this day, Lord, you'll say, well done, thou good and faithful servant, that we are able to use these 24 hours to the best of our abilities. Father, we thank you. We are standing on top of our graves and we think of those, Lord, who are bereaved at this point in time. Father, as we're about to begin our class, we pray that you grant us the added wisdom, not your understanding, so that we may comprehend the lessons to be learned. So we thank you, Lord, and ask that you will hasten the footsteps of those who might be on their way, those who are on the way, and that, Father, God, you just grant them safe passage. We thank you for all that you have done and will continue to do. Through Jesus Christ, our Lord and Father, we pray. So, on your mark, get set, go. I was looking at what it is that I was going to do in class with you today, getting some stuff prepared for you, started getting a little anxious, a little nervous, and then I said, what is wrong with you? Just relax yourself. And then in a very soft, still voice, I got a quick solution. You know, there are times we kind of think that we have all the solutions, but in the quiet and stillness of our hearts, the Lord is speaking to us. And I will tell you exactly what it is that he says to me a little later on. Matter of fact, you know, because I know I'm suffering from senior moments these last days, let me tell you from now. So what has come to mind is you all have your Unit 2, Statistics and Editable. I'm going to ask that you all start reading through so that the last 2 weeks that we have, this is where I was getting answered. We're not going to be meeting Good Friday. We're not going to be meeting Easter Monday. So that takes 6 hours, 7 hours even out of our time. And then I said, but wait, then we can go through then Editable and read through that unit. So all attention now is supposed to be on Unit 2 on Editable. I'm preparing some stuff so that we can go through. When I'm going through, I am going to bolt it. I'm going to elane it. All right. So I'm going to ask that you do what it is that you're required so that we can get it sorted out. Okay. So without any further ado, I shall begin. And we are going to be looking at, continue to look at our stationary points. I'm going to be doing a few more questions on stationary points. And when I do that, then I'm going to be moving on. My aim tonight is to finish differentiation. My aim tonight is to finish differentiation. The aim for tomorrow is do some more differentiation with the business calculus, move into stationary points. So those of you who will leave the class tonight not feeling so, hunky-dory, will be able to see some more of the stationary points. And I need to move into integration with you tonight also. So let's go. Why is this not sharing? Come on now. All right. Tell me if you're seeing the screen, please.
Yes, sir.
Nice. It's very nice. All right, so as promised, last class, I had barely glanced at this question, and that's where I'm going to start. I'm going to ask you to go through this for me. It says, given the function y equals 2x cubed plus 3x squared minus 12x minus 7. We're supposed to evaluate the coordinates of our y-intercept. I did this question pretty quickly last week. I want you to do the question on paper now. The y-intercept, remember the y-intercept, the other variable is equals to 0. The critical points, remember you differentiate the function, set the function equals to 0, solve for the value or values of x. When you get those critical values, you substitute it into the original function to calculate the corresponding value of y, and those will be our critical points. To determine the nature of the critical points or to see if it is a maximum or minimum, we have to find the second derivative, substitute the x and y value for the critical points into the differentiated function, the second derivative function. If it is positive, it's a minimum. If it is negative, it's a maximum. Point of inflection, you're going to set f double dash or d squared y by dx squared. That is the second derivative equals 0. Solve for the value or values of x. Substitute in the original function, and that will be your point of inflection. And then when you sketch your graph, all the points that would have gotten from up top, 1, 2, 3, and 4, we should reflect on the graph paper. Not graph paper, you know, it's a sketch. Sketch is different from draw. You draw with graph paper, you sketch on regular sheet of paper. All right. Now, so I'm going to ask you to.
Sir, can you go over, please?
No, what I'm saying is we're going to be looking at that function. The function y, I'm asking you to do those questions for me. And I was just reminding you.
I'm asking you to explain. I'm asking you to explain I. So you work it out.
I, the first one?
Yeah.
Come on. You're just going to put, to find a y-intercept, you're going to put x equals 0. So in the function, wherever you see, come on, you just do that equals 0. So that's like a 1 marker, because a matter of fact, you can look at it. What's the value? When x equals 0, what's the value of y? Today.
Negative 7.
Yeah, duh. Them now you know that. So the coordinate of the y-intercept is going to be 0, negative 7, because y is equal to negative 7, and you're putting x equals 0. So the coordinate of that point is going to be 0, negative 7. That point must be reflected on the graph. So you get the first mark. All right, differentiate the function for me, please. Set it equals to 0, solve, and then substitute into the original and let me know what it is. Talk to me as you are going along, please. Start now. Remember, time is of the essence. I need to finish this. I need to start the multivariable function. And I also need to go through integration. I really want to finish up integration today. That's my aim. If I can't, that's fine, but that's my aim. All right. Manisha, I missed you. I didn't see you on Wednesday. I don't want anybody to sit there and struggle. If you're there and not following, please just unmute so we can have a conversation, please.
Science of a critical point to find the differentiation of the function and then substitute it the function.
No, for the critical points, you're going to differentiate the function, set the function equals to 0, and solve for the value or values of x. Mhm. Remember, if you're struggling, don't sit down there and struggle.
Sir,
Yes, please.
sir, all you need to determine the point of inflection again.
It again, point of inflection.
Yes, sir.
You're going to find the second derivative. Find the second derivative, set it equals to 0. Solve for the value.
So what we do for I part 3?
Critical point, you're going to find the second derivative. And then you're going to
But
substitute
for part 4, we substitute 0.
For part 3, you're finding the second derivative. You're substituting the critical values into the second derivative. If the result is positive, it's a minimum. Negative is a maximum. Part 4, we're setting the second derivative equals to 0 and solve for the unknown or unknowns. And then substitute that into the original function to get the point of inflection.
Okay, sir, thanks.
How is Steve?
Finish, sir.
Finished? I didn't hear that. What was it?
Finish.
All right, so I'm projecting. Let me just reduce this a little bit. So that's my intercept. My critical point. When I differentiate the function, this is what I would have gotten. I'm just going to go through. If you're not seeing it, just say something to me. Now remember, on Wednesday, I picked up a deficiency. I have been thinking about it ever since. There are some of you in the class that are working. The 5 questions I gave on the board, you were able to consume them. There were some of you that I'm very concerned about. The basis of the differentiation is missing. What I can't understand, I am here killing up myself. Mrs. Henningham comes and she reinforces what we did in the previous class before the start of the next class. And there are still gaps with the differentiation. Vitamin deficiency, a mathematical deficiency, a lazy man writes deficiency, a not unmuting deficiency, and I'm going to say it in Jesus' name. If we do not understand, say something. I'm tired of saying the same thing over. I sound like a broken record. Me don't know what else to do. Me don't know what else to do. Honestly, I don't know what. I feel like I failed. I don't know what else to do. One of the things that was very evident was that, so for those of you who understood the formulation and was doing the first times the derivative of the second, you weren't using up your parentheses. Please just use up a parentheses so that when you're distributing one over the other, you don't make any mistake. Don't get me wrong, you know. I know there are students there that are performing. My only disappointment, Mrs. Herringham and I have been side talking today. My only disappointment is that time is against us. It's if I had from the September, from the 3 weeks or the 2 weeks in September and the month of October, I would have been in a better position than what I'm in now with just 2 weeks left. I'm being frank. But what is important is that the areas that we've already covered, when they can't go into the exam and leave out those, because we shall be crashing the other area. So it's very important, guys. I beg of you, very, very important. Hold on a minute. All right, continue. Just look at that for me, please. One second. All right. So work with me now, guys. Work with me.
So we can have 1 point maximum or 1 point minimum.
Of course.
Oh.
Yeah, man. That's what they normally come in on. They normally come on. It's because the curve. Mrs. Henningham, please close their ears now. the curves come very sexy. So them curvulus and curvulus, yeah man. So them go up and them go down. So normally when you talk about point, but let me give you a little hint. Normally when I'm teaching, I like to use the investigatory approach so that you can investigate and then ask me questions based on what I do. But because of time, let me just let out the secret. So once it is that they ask you about a point of inflection always occur between a peak and a trough, always occur between a maximum and a minimum. So once they ask you about point of inflection, one of the points is going to be maximum and the other point will be minimum. Real talk. So how do you know this? By doing the questions over and over and over and over and seeing the pattern. So I'll point out to you, no pun intended, the point of inflection, right? It is the inflection point, which really is a midpoint between the maximum point and the minimum point. It's a midpoint between the maximum point and the minimum point. All right. So it's a very sexy looking graph. Goes up, you know, and if you look at it, it also is indicative of the relationship we have with God and with friends. We're on the mountain peak, you know, you come out of retreat and fasting service and Sunday morning service, and then, you know, by the time you reach Friday, when you drive on the road and the driver them mess up your headspace and start telling them how much Jesus loves them, then they go down into a little valley, you know. So you will see what is happening there. All right, so let's continue here now. So we differentiate the function. Again, I'm going to say this based on some of the questions that some of you asked me on Wednesday. There are some gaps. There are some gaps when you're differentiating. Y is equals to x to the n. dy by dx is going to be equals to nx to the n minus 1. You use a power to multiply the coefficient of the variable for which you're differentiating, and you're going to reduce the power by 1. So it's 2x cubed, and I differentiate that, I'm going to get 6x squared. The other term is going to be 6x plus minus 12. So for critical point, dy by dx is equal to 0 every single time. When I'm doing single variable function, and you soon see for the multivariable function, it's going to be equal to 0. All right? And then I'm going to put 6x squared plus 6x minus 12 equals to 0. Now look at what I'm doing. I'm going to divide through by 6. Why, sir? So that the function becomes a little bit more easy to manipulate. I can work it as it is, but you know, when I divide it, you know, I'm going to end up with x squared plus x minus 2. Right there, and then I see the factors. 2 and 1, positive 2 and negative 1. Up top, we have to go multiply negative 12 by 6. And we don't even know that multiplication. And I go find two numbers when added will give you negative 72. And then that's just too big. So I work very smart and not hard. It's much easier for you to do that. Okay, sir. So every time I do the differentiation, I'm always going to divide through by 6. No, please. The only reason I'm dividing through by 6 is because 6 is a multiple of each of the terms, or I can say I can factor out 6. 6 can be factored out. It's not going to change it. It's not going to change it. Sir, how do you know this? I can bake 6 cookies from a recipe. I can also, from that said recipe, bake 12 cookies. If I want, I can bake 15 cookies. If I want, I can bake 17 cookies. All right? It's not changing the recipe. All right? So let's go. So recall, factorize the trinomial above. We multiply the coefficient of x squared by the constant term. And we are going to end up with negative 2. And the two numbers, when multiplied together, will give me negative 2. But when added, we give me a positive 1. And that will be positive 2 and negative 1. So my factors here are positive 2 and negative 1. Substitute that for the value of x. When I factorize, I'm going to end up with x is equal to negative 2 or x is equal to 1. Did everybody get up to here?
Yes, sir.
Very
Yes,
nice.
sir.
Excellent. Very good. Very good. What about those who did not answer? Can you see where it is that you went wrong now?
Sir, I'm coming, so
All right. Say it again. Oh, it's Natty.
No. Xavier.
JV, well, you just came in.
Yes.
Afternoon, sir.
Hey, John. All right, never mind. See if we can follow up, right? All right. Afternoon, Papa. All right, let's go. So we're continuing actually. So now that I have found my values of x to be -2 and 1, these are known as my critical x values. They are not stationary points because remember, a point is an x and a y coordinate together. That's what gives a point. An x value and a y value gives a point. So we need to now substitute these into the original function. Please, I have students over and over and over again substituting into the differentiated function. That's not right. You're substituting into the original function. Why, sir? Because they want the y values. Let me explain why you can't substitute it into the differentiated value. Because if you substitute the x value into the differentiated value, the value that you're going to get is not y. It's going to be dy by dx. The differential. You don't want the differential, you want the y value. So you have to substitute it into the original value. The original value is the only one that will give you your y. All right, so we want the corresponding y value. So put that into y. I remember what y is. 2x cubed plus 3x squared minus 12x minus 7. So anywhere in the function I see x, I'm going to put -2 in the first instant. That works out to be 13. That works out to be 13. Similarly, I am going to be doing the same thing, but this time now I'm going to substitute my x equals 1. Why 1, sir? Because that was the other critical value. And I'm going to get x to be equal. I'm going to get y to be equals to -14. So look at this now. My critical point, see here, x is equals to 1, see the 1 right here, sir. Y is equals to -14, see the -14 right here, sir. So I have two critical points. Critical point -213, critical point 1, -14. Are we all there with these two critical points? Or you need further explanation?
I'm good, sir.
Further explanation.
Further explanation. Okay, no problem with the further explanation. But tell me where. Where do you need a further explanation, please? Talk to me now, talk to me now. Like, it's not, I'm sure it's not everything. So just tell me where you want further explanation.
Yeah, the critical point are the same as turning point.
Yes, sir. Give me another name for turning point.
Stationary.
Thank you, sir. All right, so I'm asking a question one more time. If not, if no answer, I'm going to move on. So a female says further explanation, and I'm asking, where do you need further explanation? Going once, going twice.
Sir,
Say it again, Amelia.
we get 1 and -14. So what? Sir, I understand we get a -14, but how comes 1? Comes the critical point.
Because remember, these are my critical values. X equals -2 and x equals 1. So remember, a point is an x value and a y value together. A point is an x value and a y value combined together. So since I have the two x values, see there, x values, they are known as my critical values, not critical points yet, because I now need to calculate the corresponding y value for each of these critical values in order to get my point. So what I'm going to do is to substitute x equals -2 into the original function. See it right here, sir? I'm putting x equals -2 into y. But what is y? Recall, y is equal to all of this. So anywhere in y I see x, I'm substituting -2. So it's 2 times -2 cubed plus 3 times -2 squared minus 12 times -2 minus 7. And I just work it out. And I'm going to end up with 13. Remember, When I cube a negative number, my result is negative. So negative 2 cubes is going to be negative 8. When I square a negative number, my result is always positive. So negative 2 all squares is going to be positive 4. Amelia, tell me that you see it now. Amelia, talk to teacher, please.
Yes, sir, I get it now.
Thank you, thank you, thank you. All right, now let me just say something as I see more students joining the class. Time is of the essence. I think we did pretty well for the first term by completing unit 1, module 1, sorry, is the longest module. And we finished that pretty much in good time. I'm trying to finish off the second module. I just have 1 more unit to go, like 2 more units to go to finish off this module. I'm going to ask that you put yourself into a frame of mind that you're going to be able to absorb the information. I want you to be in a position to absorb the information. But importantly, let the questions continue to come. Don't have a problem. Mrs. Henningham is here. She's taking notes as per usual for the questions to come so that we can focus on those areas. But please, let them come. All right, so I do the same thing for x equals 1. And where x is equals to 1, thanks, dear miss. When x is equals to 1, I'm doing the substitution into the function, again, the original function. Why the original function, sir? Because I'm trying to calculate the y coordinate. The y coordinate. Let me just put a notation here. A point P. You see, as these things come to me, I just trying to make life so much easier for you. I hope you're reading through your notes here, guys. So a point P is always of the form. Let me see if I can remember that form now. Sorry, I'm typing. Oh, come on, don't do this to me. Get up, no. Right, so a point P is always of the form x comma y. So I can't have, once I'm speaking about a point can't be just an x value. Because to put it on the Cartesian plane, I have to first find the intersection of those two values, the x value and the y value, that will give me a point. So when I say to you, and this is why, you know, I love Jamaica. This is where I was born. I love my country. I've been to other places, other countries. I like the United States. I like them because, not for everything, but I can see maybe in a math teacher living in the United States, you know, my life would be somewhat easier because I could make a lot of reference, and especially to their monies. You know, no longer in Jamaica can I ask students to find 26 cents because we demonetize our 1 cent and our 25 cents and them something else. So when students come to me and everything them get them rounded off, it's a fault of the government. So the government can't talk to me as a math teacher to tell me, say, math teachers are not teaching the students how to do. I said, no, want to demonetize so we can go into the classroom to teach the students that. So when I'm teaching at a lower level now, I have to go. I remember one Sunday morning I was doing some lower level work with somebody. And I remember after church, I had to drive up and down and say to my friends, do you have any miracle coins, beg you some? And when I finish collect, I get enough money, about $4 worth of American money in coins. And I was able to find the 5 cents, the 1 cent, the 10 cents, the 25 cents, the $1 coin, etc., etc. So it is that I can, say, find 25 cents, find 32 cents, and we can do all of that. Now, part of the other problem now is that when I'm finding where Mrs. Henningham lives, she says, Mr. Shand, I am on Broadway Street and 54th Avenue. So once me find Broadway Street, me I drive galong until me reach 54th Avenue, because she's giving me a mile course, Broadway Street and 54. And then she's going to say to me, I am number 325. So this is where the point is. The point is X, Y. Broadway Street is X, 54th is Y. So she's given me a point to say to me, this is where you come. Once you find Broadway and 54, you can't go wrong. I am going to be on the 3rd block, the 4th house, number 325. And if you look at an aerial view of the United States, it is made up in blocks. So if you can, we tell people, once you can read and write, you can drive a foreign and you can't get lost a foreign. Because every avenue have a name. And like in Jamaica, where the man them take off the name, so you not even know which avenue it is. What's the point, sir? I can see my coordinates. And this is how they use. So if I'm explaining to you how to find Accessible Community College, I will say to you Mountain View Avenue and Deanery Road. But sir, Mountain View Avenue and Deanery Road, and they say, okay, fine. Let us use that as our milepost. So the intersection now between Mountain View Avenue and Deanery Road, I can say to you, depending on what direction you're going, one side you're going to find Selby, and the other side you're going to find a high school. Now, once you find that landmark, then I can say to you, you're going to go in another direction to 137, and that's where you find the main campus. So once you find that landmark, that point, you can find anything else. All right? And this is how I'm saying to you, math is real life. Real life. You can't live in a life without the maths. Real life. All right, let's go. So that's what my point is. All right? So now that I have my X and my Y, I have my critical points, I now need to determine the nature of the critical point. Sir, what do you mean by the nature of the critical point? This is how we do it in other calculus courses. We ask you to determine the nature of the critical points. CXC may ask you, may not use the term nature. CXC may ask you to determine if it is a maximum or a minimum. Are the same thing as nature. You're finding out who them be. Is the maximum point? Is the minimum point? And remember, I said, the mere fact, very good. The mere fact that they ask you about, the point of inflection suggests that there's a maximum point and a minimum point, right? I don't know the extent to which your math teachers for CSEC went through the parabola and explained to you what is happening in the parabola as it relates to the shape of the parabola. When the coefficient of x squared is positive, you have a minimum graph every single time, yesterday, today, and forever. When the coefficient of x squared in a trinomial is negative, you will have a maximum graph which shapes like an N for negative every single time. And that gives you a maximum value. It gives you a maximum value. Now, when you look at the minimum graph, it tells you what the minimum value looks like. All right, always a very good exercise. I'm hoping it's still there. One of the things that I tried to do in room 306B, I think, not sure, I didn't remember to look at it the other day, to the left, to the right of the wall, right by the light switch, you should see two graph papers, cartridge papers rather, depicting what it is that I'm saying to you in terms of your parabolic shape, positive and negative, maximum, minimum. All right. So in determining the nature of the critical points, whether it's a maximum point or a minimum point, I will know. I am going to be trying to find the change in the derivative, because that maximum value, the maximum value, the graph is increasing until it reaches the maximum point on the graph, and then the graph starts to decrease in value. That's for the maximum. For the minimum, starting from the left, the graph is going to decrease until it reaches the minimum point. Let me demonstrate to you what I'm talking about. Watch me here. This n is saying to me that this point up here is going to be a maximum because it's negative. My u is going to be a minimum. It's going to be positive. Look at what the negative graph says. I am increasing until I reach a point on the graph where there is no more increase. It means that at that point, my derivative is equals to 0. There is no slope. It is 0. When I move an inch from that point, it's a decrease that I'm going to be experiencing. And I'm going to have that decrease. At somewhere in here, I'm going to have my point of inflection between my maximum value and my minimum value. So your point of inflection lies somewhere right here. It's a midpoint between this peak and this trough, this maximum and this minimum. It's going to decrease until I reach where it can't decrease no more. And an inch, a milli something of that point is going to see an increase. So this is why I said the graph is sexy. Look at what it looks like. It reminds me so much of the sine graph with that sort of loop. The sine graph going this way and going that way. All right. So if you're gonna have the graph going all the way up, maximum, all the way down, minimum. All right. Now, in order to determine this, I will have to now investigate the change in the derivative. Let me see if I have that in the notes. I can. Oh Lord, I hope I can. I hope I didn't make mention of it. I didn't. I'm only giving you all of this, because I want you to read that on your own. All right. So you're actually looking at the change in the derivative. You're investigating the change in the derivative. All right. You're going to be investigating the change in the derivative, right? Nature of the turning point. So that's what it is that we're doing. We're investigating the change in the derivative. We're investigating the change in the derivative, right? Change in the derivative, what that means, sir? Oh, the slope. Yes, because remember I say it will go up, it will go up, it go up, it go up. Then after that it reaches 0, and then it will go down. So it's the change in the derivative that we are looking at. When you and I driving the country, Ochos Rios, I'm on the north-south highway, and then you're driving up. You reach a point on the hill where it is that you stop going up. And matter of fact, you and I can identify almost one of those peaks on the graph, or on the hill, because you see a notation that says, oh goodness, what was it? It's either 6% grid or 8%, right? So it tells you to the left of it, of the highway, the slope. It says the slope, I think it's either 6% or 8%, one of the two. And it says to you, drive in low gear and heavy duty vehicle, keep to the left, because the slope is at its maximum at that point. So the car is going to drag. So sometimes I'm driving and my Betsy take a little while to go over the hill. So you know what I do? I just turn off the AC a little bit so the car can get a little bit more power, and then it just go all the way up. Sometimes I'm driving on the highway. Mrs. Henningham, you can verify this for me. You're driving on the highway and you have some vehicles driving way past, like some minibus, fly past you. And I say, weird, the moment ticket. But when them reach right there, someone, and because them have enough waiting for something and them have to take them all little time go over, you just drive past them and say bye-bye. But trust me, but same way some is, same way so. But after a while now, when they're in, along the stretch, they will pass you again, right? So that's exactly what it is. Real life, real life mathematics. All right. So there are two methods. You can read through this method. I'm not going to use the time to go through this method. I'm going to use the other method of the second derivative. All right. You don't know what happened now. With all good intentions, your teacher never did both methods. I did just one. All right. Hold on 1 minute, please, guys. Give me half a second, please, guys. I'm going to separate for about 2 minutes, please. What I want you to do is, I want you to read through. Let me just reduce this one little teeny bit. I want you to read through for me what is happening here, where it tells you that's a local minimum, and then I will, and you will see what I will do for the point x equals -2, and then I'm going to ask you to try for x equals 1, the other stationary point. Give me about 2 minutes, soon come back.
Good afternoon, students. Just keeping your company while sir is away.
Afternoon, Miss.
Right.
Good afternoon.
Good afternoon. So reading what is here, what is presented here, do you get the gist as to what sir is getting at? So you have the left-hand side, the right-hand side, and it being equal. So what you're doing is to basically see how the curve is sloping and where it will level off, where it is equal to 0, where dy over dx is equal to 0. So that is what sir is doing. So he's looking for another approach how to teach you. But I'm sure just reading it, you'll get the gist of it. Because once you have the idea to say, okay, you have the turning point or you have the critical point. How is the graph sloping? Is it sloping to be a maximum? Is it sloping to be a minimum? How is it sloping? And what better way for you to determine how it is sloping than to look at how it is, where it's going to the left-hand side of the turning point and to the right-hand side of the turning point. Getting it?
Yes, Miss.
Right. And always remember the takeaway that Sir mentioned, where the negative or the positive derivative, second derivative, if it is greater than 0, is it a maximum or a minimum? Always remember that. So that will give you an indication as to how the curve, the graph is sloping, or it is. So if it is greater than 0, you know that it's a minimum. If it's less than 0, so that less than 0 as in you're getting a negative result from the second derivative. So you're getting a minimum, a maximum point when it is less than 0. One last question before Sir comes back. Why would you use the differential of y to see where to investigate the nature of the stationary points? Why not use the y? Anyone, any idea? Think about it.
Please repeat.
Why in the note here, it says that we will use the first differential and not the original function. Why are we using the first differential and not the original function to investigate the nature of the stationary points? Let me ask this question another way. When we just started differentiation, Sir says that even we're doing differentiation from when? Primary school, but they didn't tell us that it's differentiation. What were we finding when we say y2 minus y1 over x2 minus x1? What is that?
Gradient.
The gradient. So if you're finding the slope, right? And how the nature of the slope, the nature of how the curve is shaping, you'd use the gradient. That makes sense? That's what I just deduced. That makes sense, not true?
Yes, yes.
Yes, it makes sense. So we're still waiting on Sir. Anything else you have read and want to discuss, just to note?
Miss,
Go ahead.
Miss, I was wondering why on the left hand side we use -3, But on the right hand side, we use 0. Wouldn't it be -1?
Let's read the operation that we're doing. Well, the equation inequality we're doing. So we're saying x is less than -2. Any value which is less than -2. And Sir has chosen -3. You could have chosen -4. Right? Anything which is less than -2. And to the right hand side, what you're saying, anything that is greater than -2. You could have chosen -1, right?
Very good. Mhm.
So Sir is back.
No. Continue. Yeah, you're correct. Yeah. Because
Right.
I cannot sense the conversation. Why did I choose 0 and why did I choose -3?
Mhm.
Right. So I can't choose anything. As Miss says, correctly says, x is greater than -2. I could use -1, but guess what? Sir is working very smart and not hard. So when I work with 0 is so much easier to evaluate. Looking at my derivative. Remember, no, we are investigating the change in the derivative. So there's something here I look at, you notice this piece here, so is the same thing that I'm substituting right in here, so is the same thing that I'm substituting in here, so the same thing I'm substituting in here, so. So let me tell you why I am investigating the change in the derivative. You recognize when I substitute this -2, which is my critical value, what do I get here? 0. And every time I substitute it in the middle, come on, x equal 1, I'm going to get 0. Because, and that's why now I'm saying to you that I'm investigating the change in the derivative. Allow me to make some connection with what it is that you're studying, because connections are always very important, especially if you concretize one concept and I make a connection with another concept, it helps you to concretize both concepts. Remember, when we're doing limits, and we know say the limit is going to be -2, but we look to the left of it and we look to the right of it. It sounds anything familiar to you?
Yes, sir.
Yes.
Are the same something we are doing? Are the same investigation? So we know that the limit, see here, when x is equal to -2, we know -2 is a critical point. It is the point that we are interested with, and in -2, that is the point where we want to find out information. Now, in order for us to find information out for that one, we have to look to the left of it and we have to look to the right of it. That's exactly what we're doing. I'm looking to the left-hand side. I'm looking at the right-hand side. I know in the middle it's going to be equal to 0. So I have to look at the behavior this side and the behavior this side. Now, if the behavior is from a positive to a negative, then I have a maximum. Watch this. So as Miss told you correctly, x is less than -2. I can select any value less than -2. So -1, no, -1 is a bigger value than is -2. So I have to go to the left of it, which is going to be -3 is the first value that is bigger than, that is smaller rather than -2, or less than -2, when I go on the number line. So I'm substituting -3 into the function. You know what I'm interested in? Not even positive 24. I am only interested whether or not it's a positive value. The value of it is not, I'm not interested. It could be positive a half. The half does not mean anything to me. What matters is that it is positive. So if it is positive, then I know at the point it's going to be equal to 0. I need to investigate what is happening on the right-hand side. And at the right-hand side, remember, no, x is greater than 0. Miss told you a while ago. Miss say, I need to find a value that is greater than -2. I could have used -1 because -1 is greater. But you see, why I never use -1? Because I've got to say -1 squares. And I did that over here so already. So I want to run through the question because I just use my 0. I'm going to get negative. So look at what happens. When I have the change in the derivative moving from positive, you may know, this is my positive slope. When I'm going in a positive direction on the graph, this is the direction I go. Up. When I'm going up, it is positive. You step up in a life without a $20 coin because you don't believe in gambling. you are going up. At this point, when it is flat, there is no gradient. Aha, look at what is happening. The gradient is zero. The gradient is zero. So this is a positive gradient. So when we talk about gradient now, dy by dx we talk about. Dy by dx is a slope, is a gradient. So my gradient is going to be positive. This gradient here is zero. It has no slope. It's flat. It is like you walking in your house. But when you're climbing the stairs, you are at a positive slope. When you're coming down the stairs, you're at a negative slope. And then this here now is negative, that means it goes this way. So look at what happens. I go up from the left side, in the middle, flat, and then the right-hand side so that I go down. Now, somehow, don't get cheeky now, somehow this looks like the curve, it's curving downwards. This is my preferred methodology in teaching this thing. But over the years, students don't like this method, so I start using the second derivative method. So there are two methods. I like the graphical method, but students always generally prefer the second derivative method. So I most, oftentimes stick to that method, but I'm showing you both methods. So moving from positive through 0 to negative, it's going to be my minimum. So a local minimum, why? Because the shape of the sketch looks like N for negative. Now, please don't tell me that this don't look like one N. In my book, it looked like one N. All right, so work with me. You start positive. Yes, Papa.
So yep, you do them the left and the right hand something first, and then you sketch what you think it would look like.
Very good. So I have to do this piece up here first, and then I just give a slight sketch to know what is happening. So when it turns down like an N, it's maximum. When it turns, and I'll show you what the minimum one looks like. All right. In a similar fashion.
So when it
go ahead.
So when it frown it maximum and when it smell it minimum.
Very good. Very good. All right. So look at this now. In a similar fashion. Remember, we are interested in the change in the derivative. The change in the derivative. Sir, what do you mean by the change in derivative? I keep hearing saying it. Watch me. The change in the derivative is the slope. Can you say that for me, please? Say that the derivative is a slope.
The derivative is a slope.
Very good. The derivative is a slope. So look at what is happening. I am looking at a slope that is positive. Then the slope changes to 0. Then the slope changes to negative. So what it is that I'm doing, I'm investigating the change in the derivative, moving from positive through 0 through negative. Similar to when it is that we're doing a piecewise function, we go from the left-hand side, left is negative, and then we'll go to the right-hand side, right is positive. See, less than is negative. This been teaching a long time, and the right-hand greater than is positive. All right, so what we're actually doing, I think this thing here needs to be highlighted, even more than how I've highlighted it. No. We are indeed investigating the change in the derivative. It is a change in the derivative that we are interested in. All right, watch me now. Let's go again. This one, So we're looking at our x equals 1. Okay, sir. So you're saying then that x equals 1, we're doing in the middle. Yes. And then we look to the left-hand side of x equal 1. Yes. And also the right-hand side too, sir. Yes? Yes. So to the left of 1, we can have 0. Don't. Because when we look on the number line, the left of 1 going to be 0. I can use -1 too. -2, -100. But why am I going to use that? And I can utilize my 0. I'm utilizing my 0. So when x is equal to -1, remember, students, we're not using y. Why? Because we are investigating the change in the derivative. So it is the derivative that we are interested in. So when x is equal to 0 here, my value works out to be a -12. I know in the middle it's going to be 0. In the middle, I know it's going to be 0. And then to the right of it, to the right of 1, I'm going to try x equals 2. I'm going to try x equals 2. This will become 2 squares is 4. 4 times 6 is 24. And 6 times 2 is 12. 24 plus 12 is 36. 36 minus 12 is positive 24. Bam, positive. Look at the change in the derivative. I go negative because this is sloping downwards. So when I go downwards, it's negative. When I go up, it's positive. And it can use real life to recognize it. When I'm down, I'm sad. I'm losing something, my joy or my happiness. So when I go down, it's negative. The slope is 0 right here. So there is no slope right here. So, so when I have x equals 0, sorry, dy by dx equals to 0, there is no slope. That when dy by dx is equals to 0, it means that it has no slope. No slope, none, 0, zilch, nada, nothing. And then this piece says that it goes up. So there is a change in my derivative that I'm investigating from negative through 0 through positive. And this is going to be a local minimum. It's my minimum curve. And it looks like it's shaped upwards like a U. So the shape looks like a U for positive, N negative. And you can't forget that, you know, because negative begins with the letter N. All right. So I know I'm able to tell you about the nature of the points, local maximum, local minimum. All right. Now, as I said before, once it is that we're speaking about a point of inflection, that occurs only when you have your maximum, your minimum. So if you look at the question last week I could not calculate a point of inflection. Not last week, you know what I mean, Monday. I couldn't calculate a point of inflection because I only had what we had last week. I only had a minimum. There was no maximum. So there's no point of inflection for me to calculate. Sir, how do you know that there's no point of inflection? All right, no problem. Thanks for asking. Point of inflection occurs when dy by dx is equal to 0. D squared y by dx is equal to 0. And then it's solving for x. Let us look at d squared y by dx squared. D squared y by dx squared is equal to 2. And if I set this equals to 0, I'm going to have a non-equation because what it is that you're saying to me is that 2 is going to be equal to 0. Can 2 be equal to 0?
No, sir.
No. So because 2 can't be equal to 0, it means that I cannot have a point of inflection. I will not have a point of inflection in this case. Can't have a point of inflection in this case. All right. So that's why that occurs like that. So when I look at my d squared by dx squared, it will tell me whether or not I can have a point of inflection. All right, let's continue. Are you following so far, though?
Yes, sir.
Yes, sir.
I'm happy for that. Thank you. Thank you. Now, point of inflection. Remember now, point of inflection, I have to go to my second derivative. I could also go to my second derivative to, I didn't do it, but I quite frankly, I would say I'd rather spend the extra hour to develop the concept, because once the concept is fully developed, I don't have a problem moving on because you already will have that pace. So that's method 1. Let us look at method 2 now. My method 2 is by investigating the second derivative. All right, so because I never did that, let me go here. So let me copy that. Boy, if whoever created a copy button on this computer business, trust me, copy. All right, so my method 2, when x is negative 2, I'm looking at my, you know what? Let me do this thing this way. Copy. Because when I move to multivariable function, that's why I want to teach you conceptually. So when I move into multivariable function, you don't ask me, then sir, why I never did that for this one? Let me see what I do here. Multivariable functions that I'm moving into tonight. I'm going to give you one more question to do, and then I'll move into multiple variable. All right. So I'm looking at my critical points now. So it is the same thing here. I'm investigating when x is -2. Because I'm looking at a single variable function, I won't have any y in my slope. Because I'm looking at a single variable function, when I evaluate my slope, I will not have any y in it. There is no y in it. Why, sir? Because I'm investigating a single variable function. If, on the other hand, I am looking at a multivariable function, I am going to have x and y each up in order something, the derivative. So that's why I was only able to say when x is equal to -2. So my method 2, I'm going to use this terminology. Critical point, -2, -2, 13. All right? So watch me now. Your teacher loves copies. Yes, Papa.
You can explain what they say about multivariable something like that. But you get up on it.
Huh?
This is something about multivariable. Can explain about that again.
All right, we soon come. I'm going to do that in another maybe 10-15 minutes. So you'll see it. I was just only making reference to it so that when I get to it, you can say, oh, sir, this is what it is that you're talking about. I'll soon come to you, Papa. I promise you. All right. So let us look at this critical point, -213. -213 is suggesting that anywhere in my second derivative, I see x. I am putting my x coordinate. So in this here case, in that your case, I am putting in I'm typing. So in this your case, my second derivative is 12x minus 6, 12x plus 6. So anywhere in my second derivative, I see x, I'm substituting -2. So this becomes 12 times -2 plus 6. Now, as I said to you before, I am not interested in what the actual value is. I just want to know if it's a positive number or a negative number. So watch me now. 12 times -2 is -24. Now, -24 plus 6 is a negative value. Somebody else gets a negative. You know again? We say after that, LOCAL. It's negative, it's a local maximum. That's a local maximum, sir. How do you know it's a local maximum? Because it is negative. Let us check to see if our critical point when x equals -2 was a local maximum. Yes, it was. See, when x is equal to -2, we got a local maximum. Then, sir, I forgot through all of this. We got still up to the right-hand side and to the left-hand side. When you could have just do it in one line, yes, that's why I revert to doing it this way, because students gravitate to the shorter of the two methods. But the first method has its advantages and its use, because it relates to what it is that we have studied in the past in terms of looking at our limits, in terms of doing our piecewise function. And I'm showing that it's the same idea that we're carrying forward, right? And our intuitive approach also to the evaluation of our limits. All right. So whichever of the two methods you choose, it's fine. If you want to do the second derivative method, you get the same number of marks. All right. I think maybe it will be safer for some of you. So I'm checking my second derivative, but of course, you must make sure that the second differentiation is correct. All right. Likewise, the first differentiation. All right, let's go. So I'm going to substitute my -2 into my second derivative. So I'm going to end up with 12 times -2 plus 6 is a negative value. I'm not interested if a -10, 5, 4, 3, 2, 1, not interested. Once it is negative, I know I have a local maximum. I'm going to do the same thing here. Copy. I'm going to do the same thing here. When x is equals to, I think that was 1. I hope I'm correct. When x is equals to 1, 12 times 1 is 12, and 12 plus 6 is 18, positive 18. The value is positive, so I'm going to have a local minimum. Let us check to see now if when it was 1, we had a local minimum. Yes, when it is 1, x equals 1, we had a local minimum. All right. The good thing about this method, by I like, is that you'll have an idea of the shape of the graph at whichever point it is, right? Reminding you that the local minimum is going to be a curve up and the local maximum is a curve down. So method 2 is pretty simple. you know, you have your first derivative and you have the stuff, so it is that you can know what is happening right there. All right, let me just move this up here, so reduce the number of what it is that I'm using. Come on now, sir, trying to be quick. Okay, kind of figured that was going to happen. And then now I do this. OCD here, OCD, pray for me. Ah, the devil is a liar. It's all right. So which was the maximum again? This one. So and then now I'm seeing this here. I try to do this so that you can, the thing is a little easier to read for you. All right, so I'll have a local maximum here. I have a local minimum here, and good to go. I'm pausing to ask you, are there any questions? Which of the two methods you prefer?
Method 2.
Javier, Tani, you think I did expect when you say anything else? Nope. I expected this one. But as I said before, I concede my preferred method is a graphical one, which is what I did as my method 1. But this one here is quick and fast, and it always works. Both methods work. All right. So you know, whichever method you prefer, go right ahead. And also, this method, if you use method 2, you know, you're trying to find a point of inflection, you'd have already calculated d squared y by dx squared. So all I now need to do is set it equals to 0. So all I now need to do is to set it equals to 0. So that's what I'm doing. I'm now putting my d squared y by dx squared equals to 0. So my 12x plus 6 is going to be equals to 0. 12x plus 6 equals 0. And I'm solving for the value of x. So 12x is going to be equals to negative 6. And x is equals to negative a half. No. X is equals to negative a half. I want to find the corresponding y value. So which function am I supposed to substitute the x equals negative a half in to get my y value?
The original function.
Very much done. So I must substitute it into the original function, the original function, the original function. It has to be the original function, please. I must substitute it into the original function in order to get y. If I substitute it into any other function, I'm going to get dy by dx or d squared y by dx squared. I don't want that. I want the corresponding value of y. So anywhere in the original function I see x, I'm going to substitute x equals negative a half. All right. What you? I never did it. Oh, I did, but.
So we're saying in order to get the corresponding value of y, you have to
Yes.
put x in the original function.
Yeah. 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 All right. Let me. Sure. Whatever. Right. So anywhere in the function I see x, I'm going to put negative a half. So all I'm doing is I'm substituting into the function here, 2x cubed plus 3x squared minus 12x minus 7 right here. So I put in my negative a half in it, and I'm going to get all of that in it. Negative 1/2 cube is going to be positive negative 1/8. Remember, when I cube a negative number, when I raise a negative number to an odd power, it's always negative. So that becomes negative 1/8. When I raise a negative number to an even power, it's always positive. So negative 1/2 squares is going to be a quarter. And I'm going to put back this negative 1/2 minus 7. 2 times negative, that is going to be negative 2/8, which is negative 1/4. 3 times 1. Remember, you know, when I have a whole number multiplied by a fraction, it's only the numerator multiplied by. Why come, sir? Because this whole number 3 is 3/1. That whole number 3 is 3/1. All right? When I divide a number by 1, it remains the same number, right? So the whole number 3 that I have there is 3 over 1. So you multiply the numerators across. So 3 times 1 is 3, right up here. So, and 1 times 4 is 4, right in here. So, all right. So that's what we do. And then, of course, when I multiply two negative numbers, I get a positive number. Using the same concept here, this negative 12 is going to multiply by this negative 1 to give me positive 12. And positive 12 divided by 2 is going to be a positive 6. And I care about my negative 7. And negative 1/2 plus a 3/4 is going to be a half. And this 6 minus 7 is going to be negative 1. So 1/2 minus 1 is going to be negative 1/2. So my point of inflection is going to be negative 1/2, comma, negative 1/2. That's my point of inflection. And remember, the point of inflection is like a midpoint between your maximum and your minimum points. Midpoint between your maximum and your minimum points. All right, sir. So you do the sketch graph.
Look at me, please.
You want me to scroll where?
Wait, sir. Up. Yeah, right. There, sir. No, sir, you got too far. Wait, no, sir, I got too far. Thank you.
De nada. All right. Did I introduce you to Desmos Graph before?
The app.
I did?
Sir, the app.
Yes.
No.
I didn't? All right. I think this may be a good point to do it. I want you to all remember this function because I'm going to ask you to repeat it for me. 2x cubed plus 3x squared minus 12x minus 7. All right. So I'm going to introduce you to one of my favorite apps on the market. It's an open source, meaning that it's free. You know, if you download the app, you can download the app. I mean, I have the app on my phone. It's free. You know, you want to do a quick reference check, you can go and do that. Oh yes, I know what. My piecewise function. One of these days, when I have a little more time at hand, I'm going to show you what the piecewise function looks like on the graph. Right? I'm going to show what the piecewise function looks like on the graph. So I'm going to go to Desmos Graph. It's an open source, meaning that you can just go and just put it Desmos, DESMOS.com, and you can get the online version. There is also an app that you can get, you know, that you can have it stored. You can create an account that, you know, when you do your graphs, you can actually save those graphs. I kind of have an account, but I won't log into it. So you can log in or you can sign up on the whole stuff, la-di-da, la-di-di. All right, I'm going to ask you to help me out now. 2x cubed. Look at what I'm doing. I'm going to my keyboard and I need to take out that. It says 2x cubed, 2x. Then I go, because if I want square, I click on this one, but because I want cube, I click on that. It goes up there. I just put the 3. Then I'm going to use my arrow button to get it all the way back down here. So what was it? Plus 2x squared. Help me out. What was it?
3x squared.
Plus 3x. And because I want a square, I just click on this. 3x squared.
Minus 12x minus 7.
Minus 12x minus 7. Look at what I'm doing here now. I'm clicking on this thing to hide my keyboard. And then I am clicking on this to hide my expression, which is my graph. If I click on this X, I'm going to delete it. Right? So I'm clicking on this just to push it over that side so I can get my full graph to look at. No, oh my Lord. Over here, I'm going to click the negative button. All right, I think I'm going to go there. So I can see the full length of the graph. Now, this point up here is supposed to be negative 2, comma. Was it 13?
Yes, sir.
You see it right there, so? Tell me if you see the negative 2, comma 13.
Yes, sir.
Yes, sir.
Are we so bright? Are we know we're right? We know we're right because we get negative 2, 13 right up there, so. That is going to be my maximum point on the graph.
Sir, we're going to start graphing the exam, right?
You're going to sketch the graphs in the exam. Right? So this is what I'm saying to you. So the graph there, I'm gonna go up, I'm gonna go up, I'm gonna go up, I'm gonna go up, 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 until I can't go no further up. This is gonna be my maximum up that I can go. Anywhere down here, so it's gonna be down, 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 down. All right? Right down here, so now it's gonna be my minimum. Look and see if you see 1,-14 down here. So you see it?
Yes,
Yes,
sir.
sir.
That's my minimum point of the graph. My minimum point on the graph. Now, guess what happened now? Tell me if that is 0,-7.
Yes, sir.
Did we get a 0,-7 in our calculations?
Yes, sir.
Yes, sir.
What was that?
Y-intercept.
And the y-intercept is where the graph puts the y-axis. Did that graph put the y-axis?
Yes, sir.
Yes.
Yeah, ma'am. So it show me negative that. Now, what is this point here? Come on now. That's not it exactly. Okay, so what this is, what, okay, so what it is, so what the graph is giving you here, you see some gray points here. It is giving you the maximum value, -213 is giving you the minimum value, 1, -14. It is giving you the y-intercept. But believe it or not, right here, it is telling you the solution to the graph. So it's saying that when y is equal to 0, x is going to be -3.079. So if I substitute into the function, anywhere I see x in the function, if I substitute -3.079, I'm supposed to get 0 for my answer, which is a y value. Remember, no, our x value is known as our independent variable, and our y value is known as our dependent variable. So y is dependent upon the value of my x. So when I substitute my independent variable, -3.079, into the original function, best believe that I'm going to get 0. Interesting. Let me ask a question and see how many of you remember. I know Mrs. Henningham did this, and I know I came in and butted in and said something when I took over the class. How many sets of answers would I have if I were to solve this question?
Sir, 3.
Why, JVO?
Sorry, that was not J.
Oh, I'm sorry. Oops, I'm very sorry. Why? Matthew, if I clap, you say Matthew?
Sir,
Why 3?
because 3 was the highest power, the something.
And that's why I'm gonna put you across my lap and beat you when you tell me say you don't like the maths. Very good, Natty B. Sister Buckley, very nice. So remember, I said to you that the highest power in the polynomial tells me how many solutions I'm supposed to be having. See to yourself, if you never believe me now, then believe me now. That's one solution. That's another solution. And that's your third solution. All right? So it tells you where the graph intersects the x-axis. All right? The cut of the x-axis is going to give you your solution to your y. Now, my point of inflection is going to be -1/2. My point of inflection, oh, what I could do, I could expand the graph. What I'm doing is just pinching the graph, just like when you expand on your cell phone. I'm just pinching the graph to expand here. Since I don't need to show you anything else, I'm actually trying to show, right? I'm actually trying to show you the point of inflection. We got as -1/2. I just want to see if I can bring back a half on the thing. Right. The point of inflection is going to be right here. Not there. Come on. No, it's -1/2, stupid. Right here. The point of inflection is going to be -1/2. So right here, so the graph don't highlight it now, but right down here, so is a point of inflection, -1/2, -1/2. Let me reduce the graph. Look at what I'm going to do to just reduce it quickly. I'm going to go back here to the default zoom. So when I click the zoom, I don't want that. All right, I'm gonna reduce it somewhat because I want to be able to see all of that. Let me just pan it over into the middle here. So I'm saying to you that somewhere right up in here, so somewhere right up in here, so negative a half, comma a half, somewhere right up in, that's not exactly where it is. I have to zoom out in order for you to see, but somewhere right up in here, so negative a half, comma a half, somewhere like right here, so negative a half, comma a half. If you look at that point right here, so it is going to be, this point is equidistant to this point and that point down there. So that's what the point of inflection is. So I'm saying to you, stop. So I'm saying to you, the point of inflection occurs between my maximum point here and my negative point down here. So the point of inflection occurs somewhere right in here, so which is going to be negative a half, comma a half. Can you visualize what the point of inflection is now?
Yes, sir.
Yes, sir.
All right. Matthew, you understand now why we have three solutions to the question here, Matthew, if we're solving it?
Not really, sir. You can explain that.
Say it again.
Can you explain that?
Look here, look at the function up here. So it's a cubic graph, it's a cubic function. It's a cubic function. The highest power in the function is raised to the third power. So because it's raised to the third power, it tells me that I have three solutions. If the highest power was raised to 2, it means that I have 2 solutions. So because the highest power is 3, it suggests that I have 3 solutions.
So when it's a,
all right?
sir, when it's a solution, that means you talk about which part cut the x-axis.
Very good. And that's how you find the solutions.
Oh.
Because you have to know, put the independent variable x values at rest to find out the corresponding y values. Yes. Yeah, so welcome to Desmos. Can anybody give me the function for last week? The question that we did last week? Anybody can tell me what the function is?
Not sure, sir.
All right, let me see if I can. All right, I can go back.
Sir, do you mean the 2x to the 4th power minus 5 all over
No,
x? Not that
no,
one?
not that one. No,
Okay.
the x squared minus 6x plus 1. The x squared minus 6x plus 1. Let me see if I can go back to this. X squared minus 6x plus 1. X squared. Look at what I mean. I'm just pressing 2. Is it 2 right here, so? I'm just pressing a 2. X squared. Let me say again. X squared. X squared minus 6x plus 1. All right. Now, so I have 2 graphs showing on my graph. I don't want the red one to show because I finished with the red one. So all I do is just click on the red graph to deactivate it. So the graph is still, if I want it, I can just go back and click on it. Which is why I love this platform so much when I'm teaching piecewise function, because I can touch the pieces of the piecewise and take them up and put them on. Matter of fact, it's not the first time I'm using this thing, I'm going to do untruth. Because when I was doing the trigonometric function, I did introduce Desmos because I went on it to show you that the cosine graph is out of phase with the sine graph. Nobody remembers that?
Yes, sir,
Yes,
but we
sir.
now look at the app, sir.
Cute and done. Yes, but I did use this in the class. No, but I went and brought it up on the screen. But anyhow, never mind. But yes, but it's not the first time we're using Desmos in class. I was wondering why the first time, and I did so many of these things already. All right, so let me deactivate that one. Let me get this out of my way so I can have the full stuff. Now, I am looking at my minimum point here, and my minimum point is 3, negative 8. Does that ring a bell without even looking back? Does 3, negative 8 ring a bell?
Not 2.
Does 3, negative 8 ring a bell?
Yes, sir.
Yeah, man, see it right here, so. So we did a question last week when I keep saying last week, on Monday when I introduced the topic, and I used a very simplified question. And we got our critical point to be 3, -8. See it right here, so. Right there, so. And then we got our coordinate to be, our y-intercept to be 0, -1. It means they cut it at 0, -1. And we got a minimum value for our curve. Let me go back now to the stuff and share with you. See here, 3, -8. Watch it. See here, 0, -1 is where it cuts the y-axis. Sir, is there a point of inflection? No, because it's just one turning point. It has one critical point, one stationary point. All right, watch me now. How many solutions will this graph give me?
2.
2, because the highest power in this function was an x² one. You don't remember what the function is? Watch it. I'm showing you about my list. This is x². So the highest function, the highest power in the function is 2. So it tells me that I have 2 solutions. Watch me. See. One of the solutions will be 0.172, 0, and the other solution will be 5.828, 0. All right. So as I said before, very nice platform. I can use when I go to the untitled graph, my untitled graph, I can use my gradient of a line and my parabola. I can look at my trigonometric graph, which is what I use in class to show you that one graph is out of phase of the other graph. Very useful stuff. My unit circle, I can, this is what I use to develop the unit circle. Remember, I was showing you something about the unit open graph. I was showing you something about the unit circle that anywhere around here. Oh, animate. Oh Lord. Anyway, so this is how the unit circle was derived. See, it is between -1 and +1 on the x-axis, +1 and -1 along the y-axis, and then we have our half in between, and this is going to be our √3/2, half. And you know what is going to happen. We have √3/2, half, -√3/2, over this side. So it is something that when you're revising your unit circle that we've already done, you can use this in order to, to make some correlation to it.
Sir, what is the option you selected just now?
Unit circle, sorry.
No, to get the listing there. What did you select? The listing on your left. What did you select?
Oh, sorry. I went and click on the 3 horizontal bars.
Okay.
Right. And then now, if you're doing maths on campus, we do things like polar graphs. So, this was one of my favorite areas in math because, and I keep saying to you, math is real world. So you see when them people, they come out with some very pretty tiles, especially Brazil, that makes a lot of tile. Then people love maths, and they're actually using polar graphs to get designs in these tiles. I can actually animate it, and you see the different designs that are coming up. So I can animate my graph to show you what is happening right there, with it, and I can animate all of that there. So look at what is that. Whoa! I just saw Fibonacci curve. Fibonacci curve just came up a while ago in all of that. So, it has a lot of, see Fibonacci there again, it has a lot of flexibility to what is happening. And we can do a lot of explorations with what it is that we have done. Now, I was telling you that we need to do some, Jesus, Lord help me. Come next week, God's willing, when I move into statistics, and we're talking about linear regression. This is going to be my line of best fit. This is what we're going to actually be using to do our SVAs. This is what it is that we're going to generate our table of values down over here. So, and then we can use our y equals mx plus c, which is the equation of a straight line, which is what it is that we're going to be using to get our line of best fit. So this is going to be linear regressions. So something like this, maybe can use to plot a graph out of it, so forth and so on. And then I want to show you something because I don't know why it's not coming up. I want to show you something, but it's not coming up. I don't know why I'm not seeing it. Lord help me. But anyhow, I was looking for my oh, so let me just pause this here. So one of the things that if I were teaching you like a foundational 3 course that we have at the college, you will see this blue graph. This blue graph is, all right. So the graph in red is my function, my original function. The graph in purple is the differentiated function. So this is my cubic graph. All cubic graphs are those sexy graphs. And you see it has a maximum and a minimum. Let me deactivate the blue one so you can just see one graph. So this graph has a maximum. See, turns here is a maximum, and it builds up is a minimum. So this graph is one of the sexy graphs. The sexy graph I call the one. Please do not bring an examine my sexy graph. They're not going to have a clue what we're talking about. But for my sexy graph, you have a maximum and a minimum inside of it. Eh? My point of inflection look like it's going to be right at my x equals 0, y equals 0 in here. So, right? So this is my nice little cubic graph. Now, when I differentiate this graph, I am going to get this graph. That is my differentiated graph. Now, look at what will happen. This graph, the width of this graph will get smaller and smaller. Watch it. As the value of a. Come on. All right, watch it. You see that is negative. Watch it. Watch a blue graph. Negative, negative, bam. Come on now. You see when it reach at 0, it's a straight line. So why it reach 0 a straight line? Because when a is equals to 0, it means that this term, this power, is totally obliterated. So all you have is a linear function. All linear functions are straight line graph. We do all of them something we do already, All of them something we do already. So when a is equals to 0, it means that I no longer have a cubic function. This term goes to 0. All I have is just c of x. And c of x is a linear function, and all linear functions are straight line graph. Watch it, see there, straight line. Now watch when I go over right here, so now. You see what happens to a? A is fractional. You see when a is fractional, look how wide the graph is. Look how wide the graph is. When a is fractional, the graph wide. Watch this. When a becomes a whole number, the graph gets small. So was it you that I was talking to? No, I was teaching my calculus 2 students last night. And what were we doing, Jesus? Oh Lord, what were we doing? I was doing something with them. Oh, volume of revolutions. I was doing volume of revolutions. You don't have it on your syllabus. That's why I never invited you to the class. I was doing volume of revolutions. I was saying to them that if I am a potter or a woodworker and I want to make a bowl, a fruit bowl or a soup bowl, I am going to use a function where my coefficient of x cubed, the highest term in x cubed, is going to be fractional. Because when it is fractional, you see I get the width, I get the width, the width of the diameter of the bowl gets bigger and bigger, right? When I get this thing here now, 0.5, it's getting smaller and smaller and smaller and smaller and smaller and smaller and smaller. So right now I'm getting a tube. This looks like a test tube. I'm getting smaller and smaller and smaller. But guess what? When this value here becomes negative, see, turn into n. Look here, a0. And one little tubes to the left, negative 0.1, you see, turns n. So again, this concretizes what it is that we're doing. When your graph is n, it's negative, turn down. When the graph is positive, it turns up. All right. So when we animate the graphs, this is what happens. When you investigated what happens with your derivative, that's what happens, right? That's what happens to your graph. All right. Didn't plan to do all of this with you, so let me just stop here and go back to this piece here. All right. So Desmos is a learning software that I discovered maybe about 10 years ago that I really find it very useful. There are times I'm preparing questions and just have an idea what the graph looks like, and bam, you can get it. There are so many bits and pieces of investigations that you can get from it. And I mean, there are others out there, but I'm finding the ones that are very useful to me. All right. So that's what the graph, no, that's not it. So this is what the graph will look like for the sketch that we just did, right? This is a graph that we look at for the sketch that we just did. All right. Now, are there any questions? Are you following me? Are we okay? Talk to me. How we stay? How we feel?
Sir, I'm not a feeling. Me know.
So I have a question, sir.
Go
The part
ahead.
pass through the zero. What you say that name again?
When the graph passes through the zero, it's a linear graph. When the coefficient of the highest variable is equal to zero, you no longer, in that particular case, you no longer have a cubic graph. You're going to end up now with a linear function, because you have ax cubed plus cx. If a is equal to zero, that x cubed term goes, and all you're going to be left with is c times x, which is a linear function. So you're going to get a straight line. All linear functions, all linear graphs are straight line graphs. All linear graphs are straight line graphs.
Okay.
Right? Good. And it's going to be in the form y equals mx plus c. All right. I hear you, Natty. You say you don't have any feeling. I know you came class late. I need to talk to you and know why you are coming your 5 o'clock class. Your 5:30 class late. You know what I told you on Thursday? On Wednesday? In the prep room?
But I told you on Thursday, on Wednesday in the prep room.
I don't have no memory about what you told me. Anyway, I'm troubling you. All right. All right. Do me a favor now, guys. I want you to try this. I'm giving you, this is 7:33. This is the last question we're doing in class tonight. Before I move into my multivariable function, guys, I have to start the multivariable function. When I send out these notes, I'm going to send 1 or 2 questions on the stationary point. Plus, I'm thinking this is what I'm going to be doing in class tomorrow. So, Natty, I'm inviting you to class tomorrow morning, bright and early, 8 o'clock sharp.
Yes.
So you can
So you know, after tell me say I invite me, and so just send the link. My automatically now my brain say me have class pass that day.
Bless the Lord. Love the sound of it. All right. So I want you to give a try. Give an attempt to this now, guys. Please. I want you to try and try as far as you can go with this question. I'm going to give you, can I give 10 minutes? I'm going to give you
20 minutes.
Come off from a phone, JV. Push 20 minutes. Now give you, all right, 8 minutes. All right, start for me, please, guys. Start. You don't have to do the sketch part just yet, but let's start for me, please. Quick and fast. Yes, Lord.
So I'm untitled. Can't do it.
Mute, Buckley, mute. Johnny, are you working? I guess not. Tariq, are you working? Say it again, Papa. I know, I'm asking if you're working.
Yes, sir. Yes, sir. Actually, I'm not hear the name correctly, so I'm never answer.
Oh, okay, okay. So your friend, we gotta go Johnny boy. All right, cool, nice. Tariq, you working, Papa?
Yes, sir.
Is there anybody that buck up in on some difficulty yet?
Sir,
Yes, please.
sir, after my differentiate, I don't know what else to do.
Set the function, set the differential equals 0 and solve.
Okay.
Yeah.
So once you get a cubic function, which is what you're going to be getting, I think we looked at the syllabus and we saw that it's going to be cubic of order degree 3. You're going to get a cubic function. You're going to set it, you find dy by dx. That means you're going to reduce the function into a quadratic. You're going to submit it, rubbish. You're going to set it equals to 0 and solve that quadratic by factorization. That will give you your critical values. Then you substitute your critical values into the original function to get the corresponding values of y, and those two together will give you your critical points. Yes, I heard a sir coming in. Go ahead.
Never mind.
Bless the heart. Continue working. You have 5 more minutes. My side, my side, my side. Oh, we stay.
Finished, sir.
Nice.
Finished.
Anybody else finished?
Yes, sir.
JB, oh, you stay.
I still working.
You're still working. All right. Natty B, Cassie G, Matthew L, Natty D, Natty H, Shan, Foxy. All right. I give you another minute just to finish that thought, and then we're gonna move. Another minute. Finish that thought, and then we'll move. My side, my side, my side. Let's go. What are the critical points? Anybody, somebody?
-1, 7,
Negative.
2, -20.
-1, 7, -220. That don't sound right at all.
Yes, sir. That's what I got.
-220 and 1, -7. Bueno. Everybody got that one?
Sir, -17.
Yes, sir.
Yeah.
You got -1, 7. All right, let's just double check. I don't
Yes,
know what
sir,
I
and
do.
2 -20.
2x cubed, 6x squared minus 6x minus 12. Dividing through by 6 because 6 is common. Sorry, so I'm going to get x squared plus x minus 2. X squared plus x
Sir,
minus 2. Yes,
sir,
Yeah,
please.
minus.
sir, it's 6.
x minus 6x squared minus 6x minus 12.
Oh,
Because they are copy much.
leave me alone. Leave me alone. All right. I see what has happened, guys. Happiness. All right. Look. Here I have a negative sign, but here, so I have a positive sign. So that is the problem. All right, let me see how I can fix this. Good. So, you know, say everything right here, so I'll go be something different. What of 6x? All right, positive 6x. All right, so 6x plus 12. All right, what of back? All right, I know what I'm going to do. So if all of this here is positive 6x, let me copy this question and leave me alone and don't myself copy too much. Let me copy that question, change that to positive and call it one question. That will be the question for that one. And then do this and paste that right here. So, and call this example number 5, because that was example number 4. So call this example number 5. EXAMPLE 5. Oh yeah, call that example number 5. And then, oh sweet Jesus. And then this is going to be example number 6. All right. All right. And then if I'm going to do that, who you think I go sit down and write over, type over all of them something here? Not me. I work smart and not hard. Crazy. So I'm going to copy all of this now. Put it forward this now. Copy all of that. Copy. Come all the way here. So now. And click this and just call that paste. And then we just click save. And then come on now. I need to do all of this. And change here so now to a negative sign. And change this to a negative 6x. Change this to a negative. That is going to change to negative. So that is going to be negative 2 and a positive 1. So x is going to be equals to positive 2 and that is negative 1. So x is positive 2 and this is going to be a negative here. And this is going to be, oh, Father friend. Two times 4, that's positive 16. And 2 times 4, minus 12. And that's a negative 24. 16, that's 4, that's a negative 20. You got negative 20?
Yes,
Yes,
sir.
sir.
Thank you. And then this is going to be a negative. And then this is going to be a negative 1. What's a good thing? You have a good teacher. You have good teachers. Yeah? Sure. Because I don't know what is wrong with this Mr. 1. That's negative 3. And it's going to be a positive 12. Negative 3, that's positive 7. You got positive 7, right?
Yes, sir.
Yes, sir.
It's supposed to be negative 1. Negative 1. And positive 7. And it's supposed to be positive 2 and negative 20. All right, so I'm not typing program, I'm going to copy and then paste you. Positive 2, negative 20. So all of this is going to be positive 2. Sweet Lamb of God. All right, now, so let us work through this. If I use in this method, a number that is less than 2 is going to be 0. And where is my where's my differential? My differential is here, so copy. I want to follow what I'm doing now, guys. Investigate the change in f dash of x. Let me just put that there, paste. Right, so let me just paste it right here. So also paste, save. So I'm investigating the change in my f dash of x when x is positive. Sorry, it is supposed to be negative. Oh, hold on, let me just do this copy and just paste that here. Right. So I'm changing this now. So it's supposed to be x is equal to 0. So this piece is going to be negative, but this 0 is this 0. That means this is negative. So that's negative. This piece here is going to be positive. And when it is greater than 2, I call that 3. 3 is 9. 9 6 is 54. 54 minus that positive. So that we have a local minimum right here. You know, type of all of that crazy. Cut. Paste. Cut. Paste. All right, investigate a change in that when it's negative. Okay, I need to change that to be negative 1. Negative 1. Negative 1. Negative 1. And it's negative 1, less than negative 1. Oh, that's when it's greater than negative 1, it's going to be 0. That will be negative. Okay, so I have a local maximum here. All right, for the y-intercept, that don't change, but when the change is to a negative sign, you get 0, 0, right?
Yes, sir.
Point of inflection will have to change because that is now a negative 6x. That becomes 12x minus 6x. Quantum dy by dx, d double dot is equal to 0. That becomes negative. That becomes that. You got x to be equal to positive a half.
Yes, sir.
Yes.
Good job. And then I'm going to put x equals to positive a half now into all of that, into my f of x. All right, so let me just go and just copy my f of x. So let us see what my f of x is. Copy my f of x. Paste my f of x here. I just want to make sure that I'm on the right track. So it's going to be positive a half, positive a half, positive a half, positive a half, positive a half. A half squares is going to be positive a quarter. A half cube is positive 1/8. And then no, that is going to be a half. Boy, what that looks now. 2 times 1/8 is going to be positive a quarter. 3 times that is going to be positive 3/4. That's going to be a negative 6. And then a quarter plus 3/4 is a whole. And a whole minus 6 is negative 5. Somebody talk to me, please.
No, sir.
No, sir.
So it's supposed to be negative 3.
Negative.
Sir, at the top. So you have plus 3.
Oh yeah. Negative 3. Ah, come on, Sir Sean, what is wrong with you tonight? Thank you. Negative 3. Negative 3. So a quarter minus that is going to be negative a half. Negative 6.5.
Yes, sir.
Negative 6.5. Which is the same thing as negative 13 over 2.
Yes.
Yes, sir.
Oh, my father friend. It's so important it is that we don't mess up our negative numbers. Your teacher just, oh, the question finished. That was quick. That's what the question asks us, and it asks us to sketch a graph, right? All right, so you can sketch a graph 8 minutes past. You can sketch a graph afterwards. I mean, I can maybe do that for tomorrow, but I need to break right here. All right, so you all saw what I did.
Sir, can I see the step before this? For the answer for the questions before this?
Sure. That one?
Yes,
Yeah, man.
sir.
So, to be honest with you, I don't know if I'm going to have time to, but I did it. When I send you the notes, you'll see the summary. To find a critical point, you're going to differentiate the function, set it equals to 0, factorize. When you factorize, it gives you the critical values. Then you substitute the critical values into the original function. What comes out will be the corresponding y values, and together they will give you the critical points. To find the y-intercept, to put x equals 0. To find the x-intercept, to put y equals 0. Always the opposite one, you put in equals to 0. To find the point of inflection, to classify the critical points, what you're going to be doing is you can use a second differential and substitute the critical values in it. If it's positive, it's minimum. It's negative, it's maximum. To find the point of inflection, what you're going to be doing is set d squared y by dx squared equals 0. Solve for the values of x, substitute it in the original function. That gives your value, and then you will have your a while ago I said values are values, but when you do the point of inflection, it's going to be a value. So when you get your x value, you substitute your x value into the original function, and it gives you the corresponding y value, and that gives you your critical your point of inflection. Your POI is going to be the midpoint between your maximum and your minimum. All right, and then you sketch a graph. All of the information with them answer for calculating sketch a graph. They may or may not answer to sketch a graph in the final exam, but if they don't, hooray. If they do, it's not a problem. All right. And then, yeah, that's it. Set dy by dx equals to 0. And you're good to go. You're good to go. All right. So I'm taking a break from here. Let me ask you the question now. Let me stop share. Are you okay, students? Those that have joined a little late tonight. I have gone through, we call this stationary points. I have done the explanations many times over. Are there any questions before I move into my other areas? Please talk to me.
No, sir.
All right, good job. No, is the familiar no sirs that I'm hearing, the other ones are not speaking to me, and that makes me very sad. But let us move.
Sir, I'm almost getting to know. I'm almost there because I'm understanding. But
no, say that to me one more time.
I almost get it.
Very nice. We feel
Yeah,
really
after
very.
tomorrow morning.
Yeah, man. Yeah. I'm gonna see if I can. What I'm trying to do is I'm jumping around with my business calculus so that your presence will make a big difference in terms of the things that I need to cover with you and them. So I'm going to press pause on some of the other areas that I would have moved on into tomorrow that is not on your syllabus. I can just kill two birds with one stone. I'm notorious for doing that. I'm teaching a course and inviting students here. Lord Jesus, if excess ever find out. Jesus, help me. All right, let's go. We are doing this. God has given us the capacity. Say it again, not to be.
You take the break already?
Yes, miss. You come class later, one more break. Remember what I tell you, there's something? Oh, yes, miss. Can I tell you it's been recorded? I just killed myself. Oh boy, I'm telling you, these online classes being recorded. Natty B, prep room. All right, let's go.
Sir, please stop it.
Leave me alone. Leave me alone, Natty B. In Jesus' name, leave me alone. All right. So here goes. We're still on differentiation. We're still on differentiation. Still on differentiation. But this level of differentiation is going to be my partial derivative. Partial, yeah. I am not differentiating everything as completely. It's only a partial derivative. So where we're going to go with this, sir? Same place where we just left off. Stationary point. We are going to be, we won't necessarily sketch the graph of this, but all right. So as per usual, I normally give you an introduction to the stuff. I'm not just going to jump in. So let us say for argument's sake, Toyota has developed a formula for the manufacture of their Mark X and their Camrys. Mark X and their Camrys. And so there is a profit function. And they want to determine what value, meaning the number of Mark X's and the Camrys to be manufactured to maximize their profit. So this topic here is like optimization. Everybody goes into a business to make a profit. And I keep saying, oh yes, I have that to do with it too. But that's when I move into integration. All right. I keep saying, there are times I'm at work and I'm hungry and I don't want no food from where it's been recorded as Miss reminds me. Don't want no food from them. And I never carry my lunch. So I say, you know what? Jump into Betsy and go to New Kingston, and I'll go to like John R. Wang for argument's sake. And I say, walk up and down in the supermarket, get little AC into the bones, and I say, what am I going to buy for my lunch? And I say, what is a good time not to go to the mezzanine, go eat them grease up food. I'm going to eat healthy. Yeah, man. Yes, miss. Healthy living. And funny story, as I talk about John R. Wang, I remember I was a Horlicks baby. My mother better make sure she give me Horlicks for me for my bed at night time, or else me not sleep. All right. And if there's no Horlicks, she better give me Milo. Real talk, I'm telling you, And I remember when I was much younger, I said to myself, the first paycheck I get, I'm going to buy me a bottle of Horlicks and a tin of milk. And I'm going to drink my Horlicks tea in the morning. I'm going to drink my Horlicks tea in the middle day. And I'm going to drink my Horlicks tea at night. I want it cold some days, and I want it hot other days. So me, get one little work on New Kingston. The people them bank. And the first paycheck get, me just change the check there. And walk straight over to one big bottle of Horlicks and one tin of milk. And make how old? I had just left UA. So, in the early 20s, I think, or mid-20s, thereabout. Yeah. And I bought me my big bottle of Horlicks and I couldn't resist it. I went back to office and I put on some water. And I opened my thing or something. I never opened the milk because they had milk in the office. And I opened my bottle of Horlicks. I wrap it up back in a little standard bag them time there. Miss, leave me alone. No, serious. This is real talk, And I mixed my Horlicks before I went back onto the line. And I'm telling you, it was a moment. And I went home and I showed my mom, and she said, that from ever since she said the first paycheck you get to be in by the store. And I did it. No start, there was an affinity. But anyhow, that's not what I wanted to tell you. It just brought back memories. So I used to go down to John R. Wang and I used to just say, what am I going to buy? And I walk along and look at the freezer and I see them say, if you buy one yogurt, they band like about 4 yogurts together. But through me smarter than them, so the yogurt them about to expire. So when I look on the expiry date, I say, boy, it's going to expire in another 2 days. And I said, but teacher never eat 4 yogurts. I may eat 2. I am going to buy the whole 4 and go to work, and I'm going to bless 2 somebodies with 1 yogurt each. And that's what I do. Sometimes I'll buy and I say, you know what, it's just 1 yogurt I want. And I say, come, make sure you eat it today or tomorrow morning, because it'll expire the next day. Eat up with something. Now, as I'm saying this to say to you, nobody goes into a business without to make a loss. You see, when the man them band them something there, don't think them a lose here. So what they will do is buy like 4 cases of the yogurt. You see, by the time them done sell off 1 case, they make them profit. They make back the money rather, right? They make back the money just selling 1 case. You see, the other 3 cases is profit for them. So if they sell 2 cases and 1 case is going to go bad and they're going to give it that 1 case, they are not losing. They're not losing, right? And this is why when you go to banks and they talk about loan amortization, when you take a loan, trust me, you're paying the interest first. You think of the principal you pay first? So think of you taking a mortgage, a mortgage. And when you take that mortgage and you borrow $5 million from the bank, then give it 30 years to pay back the $5 million. 30 years. But if you go buy a $5 million car, they give you 10 years to pay for it. So why can't I pay back that $5 million in 10 years, like I'll pay back the car in 10 years? But the bank is charging me 30 because it's loan amortization. So what they do, they put on a whole heap of money on something. So when you don't pay them, you know, you have $5 million, you have to pay them like $20 million. Right? So this is what it is. So when you look at your multivariable function, they are able to estimate what their profit will be before they actually sell the product. This is what the banks do. When the banks are selling you loans, I can tell you, I was very closely associated with them. When the banks are selling you loans and you go in there and say, you know, I want to buy a car, but I am $200,000 short. The people in the bank will tell you, say, no, don't use up your disposable and take the $200,000. Let me lend you the money to buy the car so you can have that liquid, and they will tell you how much anything can happen and you won't want your money. Make it stay, man. Come, we can lend you the $3 million to buy your car. The bank loan you $3 million. You see, the moment the bank click approve, the bank can tell you how much money they are going to be making from you. And I'm serious. And sometimes when you borrow something, the bank is making you to borrow like a car loan. It's different from the mortgage. You're taking a car loan. Sometimes the bank is making like $1 million+ off you just by paying them on a month-to-month basis. All right. And if you're paying, and you have to check to see if it is a reducing balance that you're paying on, or your loan amount is fixed, right? So all of these are the things you have to do. This is where the multivariable function comes in. So when I borrow a loan, when I buy a loan from the bank, it means that I can use my thingy here, my multivariable function, and tell you, am I going to maximize? Am I going to minimize? What is happening here exactly? All right. So let me share this screen and just show you something. But before we do all of this, we will need to know how to do our partial derivative. Where am I? We need to know how to do a partial derivative. And what I want you to do for me is using the examples that I'm telling you. Nobody goes into a business to make a loss. I want you to use that concept to understand now our partial derivative. And what we're looking at is first order partial derivatives. I think your syllabus, and I'm going to double check, goes up to second order partial derivative. All right. But we're going to be looking at our first order partial derivative and cross partial derivatives too. All right. So we're going to look at cross partial derivatives as well. I want you to watch me. Nobody don't blink, please. Not take. Work with teacher. No blinking. Look at this. It is called a multivariable function because I have x and y. Earlier on, I had a single variable function, so I give you f of x. This one is a multivariable function, so you have f of x comma y. If I was teaching another course, you'll have f of x comma y comma z. But thankfully, it's just x comma y that you have. So I'm talking about 2 variables. My multivariable function f of xy is defined as 4x cubed y squared plus 5y squared minus x to the fourth plus 9xy squared plus 2. Then I'm supposed to evaluate f of x, f subscript rather of xy and y subscript xy. Don't get alarmed. And when you work with me, I'm going to show you the correct way, and then I'm going to show you a shortcut way. Watch me. In order to evaluate f subscript x of xy, it means that I'm doing the first derivative with respect to x. That's what this means. The first differentiation, the first partial differentiation with respect to x. The one here is the first partial differential with respect to y. Then, sir, how you will know says first partially talking about and not the second partial? If I'm talking about the second order derivative, you will see something looking like, oh Lord, you see something looking like this, fyy. Fyy means the second order partial derivative with respect to y. And fxx, see here, second order partial derivative, right? So my second order partial derivative will be my f of xx. I can have a cross partial derivative, which is a second order cross partial derivative, which could be f of xy or f of yx. But we're going to get to that. I just wanted to show you that portion there. Watch me, please. I'm evaluating my first order partial derivative with respect to x. So it means now that everything else, my y that is going to be a constant. What is the differential of a constant again?
0.
It equals to 0. Very good. So for those of you who didn't remember, the differential of a constant is equal to 0. Now, if I'm finding my first order partial derivative with respect to x, it means that my y is a constant. When I'm finding it with respect to y, which one is a constant?
X.
Very good. Happy that you got that. Watch me. Lord, how should I do this one? Okay, all right, I'm going to do that for you. Thank you, Lord. Watch me. 4x cubed y squared. This x cubed is married to a y squared. Why is it that, sir? Because the x cubed comes with the y squared. Also, like a product, so you can't separate these here. So guess what will happen? Because this one is married, anywhere the x goes, the y goes with it. So watch me, I'm differentiating, I'm finding the first order partial derivative with respect to x. It means that my y is constant. Watch this, I'm putting back the y. You notice this is y squared and this is y squared? Talk truth.
Yes, sir.
The y's don't change. No, because I'm talking about the first order partial derivative with respect to x, it means it's only x alone I'm going to differentiate. When I differentiate 4x cubed, what am I get?
12x squared.
All right, so see the 12x squared here, so? So when I'm going to put back the husband now with the wife, I'm going to have 12x squared y squared. Bam, this is my first order partial derivative with respect to x of this multivariable function. Remember, when I'm differentiating with respect to x, my y is constant. When I'm differentiating with respect to y, my x is constant. It's very important that you have your subscript to know which you are differentiating with respect to. Let me go again. Somebody missed that one. My x is married to the y. So why is that? Because the x and the y comes together as a product. So because I'm talking about my y, I'm differentiating rather with respect to x, it means that the other variable is going to be a constant. I'm going to leave it alone. So because it's a constant, I'm going to write it back. So why you write it back and the differential of a constant is equal to 0? I'm going to show you because I want you to understand it. But because it's a constant, I'm telling you, write it back, put it down, and then differentiate the variable in question, which is going to be 3 times 4 is 12x squared. You're going to have your 12x squared y squared. Watch me. My second term is y. This one is single, no marriage. What is the differential of this one, therefore?
For x, sir?
Yeah,
Sir.
0.
0 because this is only y alone, don't it?
Yes, sir.
Yes, sir.
So this goes to 0 because it's a constant, because there's no y. This is not married, this is single. And then no, this x to the fourth, negative x to the fourth is single, but is the right one we want to talk about. So this one going to be negative 4x cubed. Can you see that?
Yes, sir.
Yes.
It's right here, so negative 4x cubed. Now when we go to the 9xy squared,
Sir,
what
I
is
don't
that?
see it.
You don't see it. All right, watch me again. All right, let me do it the other way. Copy. Paste. Let me just do it with one of the terms. Let me do it with one of the terms. The first times the differentiation of the second.
Wait, never mind, sir. Me see it.
No, I'm not going to show you again. You make me start it already. I'm happy that you see, but I'm going to continue. Copy.
Show me also.
Say it again, Papa.
So me also to show me.
Yeah, man. I'm give me half a second. I'm actually typing. Me knows me teaching, you know why? Whenever I teach long, my throat gets very dry. And I kind of feel like I'm in a face-to-face class of first times the derivative of the second plus the second times the derivative of the first. This is going to be 12x squared, 12x squared. All right, don't finito. All right, so this now is going to disturb this thing here. So let me just put this up top here as my precursor to the thing. All right, so what I'm doing here, oh, come on, Sir Shan, you are doing the first partial derivative with respect to x. You have to indicate that, Sir Shan. All right, so look at what is happening here now. I'm finding the first partial derivative with respect to x, but I'm only using the first term. I'm not doing all of it. I'm only using the first term, which is my 4x cubed y squared. Now it's a product. Now this is how I would have taught you the product rule. First, 4x cubed is the first, times the differentiation of the second, then plus the second times the differentiation of the first. The first, see here, 4x cubed, times the differentiation of the second is not 2y. How you know, sir? Because I'm differentiating with respect to x. It means that y becomes a constant, and the differentiation of a constant is equal to 0. So I write that 0. Then I'm going to say plus the second plus y squared, because that's the second, times the differentiation of the first. Nobody can differentiate the first because it is respect to x. 3 times 4 is going to be 12x squared. This times this goes to 0, so I'm only left with the y squared times 12x squared, which is going to give me 12x squared y squared. See here, the same thing as my 12x squared y squared. The truth is, we don't want nobody to do the question that way here. We know how to differentiate. We are big people. We can do things mental now. We can do our stuff or calculations mentally. Do me a favor. Take a minute and look at that and tell me if you see if that methodology rings a bell. The first times the derivative of the second plus the second times the derivative of the first. Does that ring a bell?
Yes, sir.
All right, Johnny, how you see, Papa? You good?
Yes, sir. Yes, sir.
Nice, Papa. Very, very nice. All right. So let me go back to how it is that I want to look at the question now. How it is that I want to view the question, and this is how I'm going to be doing the question with you. I'm looking at my multivariable function in xy. I'm finding the first order partial derivative with respect to x. I'm finding the first order partial derivative with respect to x. It means that I'm differentiating the function with respect to x. Since I'm differentiating with respect to x, it means that y is constant. All right? So because y is constant, I'm going to write it back. So this y squared, I write it back right here, so. And then just differentiate my x. So it's going to be 3 times 4 is 12x squared, y squared. So it's so quickly I do this one, I have to write this in 3-4 lines. This one does it quick time. I'm finding the first order partial derivative with respect to x. So any standalone with y will be 0. So because this is just y squared, y alone, 5y squared is 0. All right? This standalone with my x, I can differentiate because it is x. So negative x to the 4th is going to be negative 4x squared. I mean, cube. See it right here, so? This one here is also married. So what I'm going to be doing, because I'm differentiating with respect to x, and I have a y squared here, I'm going to write back the y squared. I'll write back the y squared, and then I'm differentiating 9x. And the differential of 9x is simply 9. So my term is going to become 9y squared. And the differentiation of a constant is always 0. So this is my first order partial derivative with respect to x. We want you look at that and tell me is that difficult. And I want you to speak honestly.
So sir, you never differentiate the 5y squared.
Yeah, but it's 0 because I'm differentiating with respect to x. So the y now becomes a constant.
Okay, so okay.
Everybody see that so far?
Yes, sir.
Yes, sir. Just see.
All right. Very, very nice. If you just see it, hooray. Watch me now. Watch what I'm going to do. I'm going to find the first order partial derivative with respect to y. I just want to do maybe about 2 or 3 with you, and then Mrs. when you do a quick revision with you, right? But just work with me. You can pick up this in a jiffy. You can pick up this in a jiffy. I promise you. Let us look at the first order partial derivative now with respect to y. Let us look back at our original function. Or f of xy is defined as this. I'm differentiating now with respect to y. Which one becomes my constant now?
X.
Very good. So my x, because it's a constant, I'm going to write it back. So this 4x cube, I'm going to write it back. See here, so magic. I write back my 4x cube. And then now I need to differentiate this y squared. When I differentiate y squared, what do I get?
2y.
See here, so times 2y. I finish the first piece, I'm going to move to the second piece. Oh, but sir, you're differentiating now with respect to y. So this becomes 10y. Talk truth.
Yes, sir.
Teacher, 10y. This one here, I'm differentiating with respect to y. So this becomes
0.
0.
Right, 0. And I'm differentiating with respect to y. So it means that my 9x is a constant. So I'm writing out my 9x. See the 9x here, so I'm writing it back. And then I'm going to differentiate the y square. I'm going to differentiate y square, I'm going to get 2y. See this? Times 2y. And of course, again, the differential of a constant is equal to 0. This one I write in 2 lines because I wanted to show you that I'm going to now fix up this and say 4 times 2 is 8 and x cubed times y is x cubed y. Normally in mathematics, we write things in chronological order, in alphabetical order. So we don't write y x cubed. But sir, would that be wrong? No. But for presentation purposes, we write in chronological order, meaning that, date-wise and in alphabetical order. All right. So I'm going to write my x first before I write my y. And then, of course, this is going to be 2 9s are 18, 19x, 18xy. 2 9s are 18, and I'm saying 19. 2 9s are 18, it's going to be 18xy. And that is my first order partial derivative with respect to y. Tell me, do you think you can try one on your own at this point?
Yes, we can.
Sir.
Yes, one.
Sir, when the x and the y are together in one, like you have 9x.
Like a product.
Yeah, like you have 9xy, you'd put, and you're finding the x, you'd put by the y, but if it's by itself,
it's 0.
And you're finding x is 0?
Very good.
Okay.
Because it becomes a constant. It is a constant. So it is a constant and it stands alone. If it's a constant and it's single, throw it out. But if it's a constant but it lives with somebody else, you have to carry it back. Got me?
Yes, sir.
All right. Now, hear me. Let me just say something before I give you one to do on your own. Um, let me let me tell you something here. My first order partial derivatives are not difficult. I'm telling you straight up. You can do the question in one line. So CXC may give you 6, 7, 8 lines on the paper. You can do your stuff in one line, or worst case scenario, do it in 2 lines, and you pick up your 4 marks, because questions like this come for 4 marks and 5 marks. So you save time if you just understand how it is that I'm showing you. So you can move on to some other difficult questions. Watch me. When I'm finding my first order partial derivative with respect to x, it means that my y is constant, and the differential of a constant is equal to 0. So when that y stands alone, it's going to become 0. But when the y stands with somebody else, I have to write back the y. You get me?
Yes, sir.
All right.
Yes, sir.
All right. Let us see. Come, Johnny boy. Terry, you just not, talk to me. I mean, I know what to do you. All right, let's go.
What you
Talk to you, sir.
Not understand, man.
Talk to me, man. All right, try this one for me, please. I want you to find the first order partial derivative of x and y in this new function. I want you to try. On the mark, get it, go.
Sir.
Yes, I'm right here. Go ahead. Finish?
Yes.
Okay. You want to share your answer?
No.
Javier Campbell.
Make
Please
them
do.
do.
All right then. All right, fair enough. All right. Sai taught me. Share it with me in the chat. Oh, but then again, I may not be able to get the cube. It's all right. It's going to be too much for you to type. Zoom can do this. One of my students did this in Zoom, and I need to ask him how he did it. He sent me a picture via Zoom. I'm going to ask him, because I was going to say to you, Zoom should be able for you to just take a picture of something and just like a screenshot of something and send it out. He did it to me once in class, and I was able to go into my chat and get it. Come, guys, 2 more minutes. Johnny, you finished?
Not yet, sir. Not yet.
Matthew, how is it?
Yeah, I'm not finished yet.
All right. Tariq, how is it?
Not finished yet, sir.
Okay. I have to call upon because one Mrs. Henningham start on me again. So I'm going to make sure I call upon her first. Natty D, how you stay?
Sir, not finished as it.
All right. I'll get mute. Oh my Lord. Cookie can't cook. I love it. 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 Okay. Very good. Very good. Very good, JC. Nice. Oh Lord. All right, guys, it's taking way too long now. Like, seriously?
Finish.
Natty D, tell me your answer, Natty D.
No, I'm not sure my answer. But
Type it in the chat, Natty D. Natty D, share your answer now? Sure.
no, sir.
Think there now. Natty B, you finish?
Sir, you share your answer first and then I'll tell you if I got it right.
You remember what just happened to you a while ago, Miss Hitchman?
Yes, sir. But yes, all right. So you're not to blame.
Oh, goodness. All right, let's go. So I am getting that as my answer. Tell me if you agree with me or disagree.
Agree, sir.
I agree,
Very
sir.
nice.
That's
Okay.
Very nice. Matthew,
Yeah,
what you
for
say?
the
Make your
second one.
very nice. Yeah, no. What about the second one, Tani?
Sir, half right for the first one, but I got the second one.
Okay, all right. I'm coming back to you, Matthew. What I heard you say something, Matthew. What you said?
Yes,
Oh, okay.
Tariq.
Oh, it was Tariq. Oh, sorry, Tariq. What were you saying, Tariq?
Yes, I got you.
Oh, very nice, very nice, very nice. All right. Somebody's coming in because I need to go back to Tani.
Sir,
Yes.
I never said why weird part.
Oh, you never see this part here, this y squared part? Oh, for the second one.
What's the squared?
Oh, you never see the squared. Okay, all right. Aniki, you're very quiet tonight. Your silence is deafening.
Yes, sir, that my good.
Okay, thank you for lightening the atmosphere. Tantan, you say you get the first one, something wrong in the first one. What did you get wrong in the first
Sir,
one?
I
And
never
how?
differentiated the x to get the one.
Oh, okay. All right. Yeah, man. So it's very important that we differentiate the stuff in order to get it. All right. Let me ask a question because
Second one, I forgot that the y was a constant.
yes, you have to remember. But guess what? It gets better with practice. It gets better with practice. All right, I'm going to do one last one, and then we do a quick revision on something. Let us look at this example. Let us look at that example. It says, given that f of x is equal to all of this, I don't want you to work it out. I want you to tell me what my first order partial derivative with respect to x is. Let me call upon Amelia. Unmute for me, honey bunches. While the rest of you will work it, and Amelia is going to talk to teacher. And I'm not putting you up to embarrass you. It's a family, and I want to know what it is that you know. So you are going to differentiate the first piece for me. I'm going to call somebody else to do the other piece and so forth and so on. We're talking about the first order partial derivative with respect to x. Differentiate the first term for me, please. First order partial derivative with respect to x and tell me what you get. Come now, quick.
There was 6x.
You're differentiating it with respect to x.
I was in class and I was teaching that topic in.
I just started teaching it just a while ago.
Yes, sir, but my Wi-Fi come out, so I'm joining back probably like after 8.
All right, fair enough, fair enough, fair enough. Aniki, unmute please. Come on, Aniki. John Mark, unmute for me, please.
Yes, sir.
All right. When I differentiate this multivariable function, first order partial derivative with respect to x, what do I get?
12x y to the 3.
Is he correct, guys?
Yes, sir.
Very good. Why, Johnny? He says 12x y cubed. Very good, Johnny D. Johnny S. Proud of you. Natty B, come, your turn. I'm differentiating this with respect to x. What do I get?
Sir, 8y to the 4th power.
Very nice, sweetie. Very nice. Kesano, I'm differentiating this with respect to x. What do I get?
X.
I'm differentiating negative 5x squared y with respect to x. What do I get?
X.
10x, what mean? Incomplete. Incomplete. On the right track, but incomplete. Can somebody help her out, please?
Sir,
Why?
he gets a 10xy.
Okay. Yes, Kesana, I heard it coming with a y, but something else is missing. Somebody just came in and told you. Look at it again. Can someone just tell her this for me, please? Somebody help her out for me, please. Anybody?
It's supposed to be negative 10xy.
Very good. Thank you, Tantan. Kesana, I'm proud of you. I'm proud of you. You know why? Because I know you were struggling with the differentiation. Now, when I hear 10x, we said, no, whoa, this is nice, right? But so what we need to remember that is a negative 5x squared. So when I differentiate all of this, we get a negative 10x. I know it's coming on, and remember the y is constant, so you need to write it back. So it's going to be negative 10xy. And what is the differential of this one? Anybody? Somebody?
0.
0.
Very good. So what I don't even, I have it right. So this is what we'll get for the answer. 12xy cubed plus 8x to the 4th minus 10xy. That's what I get for the differential with respect to y. Anybody agrees with me?
Yes, sir.
Very good. Thank you, Jay. Shanti? Anybody else?
Yes, sir.
Very nice. Oh, Monisha, you're talking to me finally tonight. Very nice. Very nice. Very nice. Yes, Tati, I see that. Very nice. Very nice. All right. What I'm going to do is I'm going to take a break. Miss has about 10 minutes to just talk to you through some, maybe 1 or 2 of the things that she wanted to highlight. She had actually prepared something. Miss, I'm sorry I went over, but I needed to get to this point. What I'm going to do, I'm going to send you some questions, guys. While Miss is doing her stuff, I'm going to send you some questions, the notes and all, so you can have some of these things to practice for tomorrow. If it means that I have to put in a breakout room tomorrow, I will do that. All right, Miss, I'm going to stop share so you can just use another 10 minutes to just, and thank you guys for giving me the time to just, maybe talk about your one or two concepts that you want to bring home to them. Thank you.
Thank you, sir. I'm just going to allow us all to unwind because it's a lot of information. It is a lot of information. So any questions based on what we have just covered? I've prepared a document on the stationary point, critical point, the maxima and the minima, right? But based on what I'm hearing, you guys are getting it. You have gotten it. Just in need of some additional practice, right? So just unwinding, what have we learned today? To take a breather, let us just think about it, everything that sir has done, right? Everything that we have made a connection with, the whole stationary point, where it is, everything, how to classify or describe or a graph, right? It's a lot of information. So we're starting the ball rolling. We're starting us off. What have you learned? What point would you like to leave with us tonight? Go ahead.
If the graph shape like n is negative, and if the something less than 0, then it's the maximum. And if it's more than 0, at the minimum something.
Minimum something. Speak properly, man. Because you know that you're saying the correct thing. There's something, but she knows exactly what she's talking about. I know that it will not be writing something in the exam. Okay, but I understand what you're saying. Thank you. The maxima and the minimum. The maximum and the minimum point, right? Where is the graph? Where's the slope of the graph tending to? Anything else?
Let's say use the second derivative to find one of the, what is it called? Intersection point. I don't know. Inflection point.
The inflection.
Yeah.
Okay.
For the x value.
Okay, Taniel. So the inflection point. Okay. Who was that speaking a while ago? Who was that came on just now? Natty. Right. What were you adding, Natty?
Yes, I was going to say that when it's positive, the sketch of the graph go smile, and then that means it minimum.
When it's positive, okay, accepted. That means it is minimum. The smile goes down or up.
It smile, Miss, is not a frown. When it maximum, it frown.
Well, probably I'm imagining okay. I understand what you're saying. I was just shaping my mouth the wrong way. Okay. Anything else? So once it is greater than 0, it's a minimum. But what is greater than 0 and what is less than 0? What are we talking about?
It's the critical point. I don't know.
You don't know. So, but we've been using this term. We've been saying it. We said the inflection point, which is the midpoint on the graph, it can be viewed as
Yes, if the second derivative greater than 0. Minimum. So,
no, sir. Matthew, you save us. Very nice. So it's the second, repeat that for me, Matthew. I'm not going to say it. You say it.
if the second derivative greater than 0, it's minimum.
Okay. And second, finish
If
it
less
up.
than 0, maximum.
Okay, so we all know what we're talking about now. That's something, right? Matthias put it into focus for us. Anything else we are taking away from this class? What about the partial derivative? And before we go there, for the stationary point, why is the derivative equal to 0? I'm just thinking. Anyone?
Repeat, miss.
For the stationary point, why is the derivative, the first derivative, equals to 0? Why do we equate it to 0?
Miss, so we can factorize it.
So we can factorize it? Factorize it, and what else? What else? So when we factorize it, what are we finding?
The critical point.
Right, and we're saying at the critical point, we're equating it to 0. Why are we doing that? What can we visualize?
To find the x values to input into the first function to find the maximum and minimum values.
Okay. The maximum or it's not the maximum or minimum, it's a stationary point, right? Right?
Yes, yes.
Right. So I'm just trying to put a visual picture, just to imagine that picture in my head. When I find the first derivative, right? And we're equating the derivative to 0 at the stationary point. How does that part of the graph look? I'm just trying to remember. Can somebody remind me? How does that part of the graph look?
Miss, please repeat.
When we differentiate y, right? And we are equating it to 0 to find the stationary point, the x value, right? How does that part of the graph look? Describe it in your own words. How would you expect it to? Would it be increasing? Would it be decreasing? Would it be going up, down? Would it be flat? What does it look like?
Yes, it will be increasing and it will form a slope.
It would be?
Increasing and it would form a slope.
Can I tell you that it should be flat? It should be, remember the example that Sir was giving to say that it's where we stand still, right? So it changes direction, right? This is, right, I'll let the summary here. So at the stationary point, the gradient of the graph, we're equating it to 0, right? So this is the first derivative. And we're saying the tangent to the curve is parallel to the x-axis. So that's why you're getting the gradient to be equal to 0. You're equating it to 0. You're seeing that?
Yes, miss.
Right, so hence the graph here, see, as it comes to the stationary point, that's when it stops increasing or it stops decreasing and it changes. It changes the direction from positive. This is going from negative to positive. It's going up, okay? So that is my takeaway from class. I remember sir saying that. That is my takeaway from class. So here we go. This one is more, you can see this better. So see it flatten out? Remember sir graph where he had it flattened at the, it's like, what did he say? He zoomed it in for you to see the flat surface and he equated it to 0. That is exactly where the stationary point is. That is what he was calculating. All right. So anything else we're taking away? No? Or we got so much, we just need to settle and, you know, bring back things to our memory and redo the questions and see how best we can, you know,
We're gonna need
master
a
what
break.
was, yeah.
Miss, when we're doing the partial cross thing exercise, something when them married or them don't married, when in regards to X, Miss, Y is constant and then the other way around, X will be constant.
Okay, so when you say that Y is constant, what do you mean? Just expound, what do you mean? So if I see 2xy squared and I am saying it's a partial derivative of x, f of x, right? What does that mean? How would I interpret it? You're saying that it's a constant. So when I differentiate
Means
it,
that I differentiate X and then I put back the Y.
all right, okay. Differentiate the x and you put back the y. And if I only have y as the y in that item to be differentiated, what will be the response, the result?
Miss, I can skip over it because I 0 when I need that part there.
It tends to 0. Okay. Anything else? Thank you very much. All right. Anything else? I think the 10 minutes as fast. One final thing. There any other takeaway from class today? Let me think. Go ahead, sir.
No, I'm just saying that. Oh, I thought I thought I heard something. Yeah. So you have finished your thought, Miss?
Go ahead. We are thinking. Tati?
Miss, I don't have anything to say to what you are saying, but sir, the YouTube is still blank.
You know, to be honest with you, my thing said, all right. What time is it now? 9:06. What I'm going to do, I'm going to call one of my computing calculus 2 students who are doing their bachelor's in computer science. Let me call one of them now and bother them to see if they can assist me with it, because definitely I need to sort it out. So give me until tomorrow when you come to class. I will give you some answer. That's all right?
Sir, yes, sir.
Yes, please.
Sir, so you can make one canvas, not, what is that name? Yes, canvas, and put them on it.
I prefer the, it's a YouTube channel. You can always have it at any point in time. You just go to YouTube and just put in a stuff.
Yeah, true.
Yeah, man, they just get it anytime. So I'm gonna sort it out. All right, come guys,
Your comment, sir. You were saying you were going to comment.
Oh yeah, oh Lord, I've seen a moment. All right, yeah. So you know, as I listened to what Miss was doing with you guys, you know, just recapping what it is that I would have done. to give me a little break. I'm sitting here and I'm saying to myself, you guys are really committed. I can't complain. The only thing I can complain about the class at times is, you're not the first to unmute to speak. But in terms of coming out to class, yeah, man, you guys are there. And I asked you for a half an hour. Well, I took a half an hour from you on Monday and wanted to do the half an hour starting today, and you guys graciously gave us. I was able to put a lot of stuff in it for tonight. Miss did some revision of what it is that we did. I sent you the notes just now because I'm committed to the process. Miss is also committed to the process. So while she was talking, I was cutting and pasting and doing all what I'm supposed to be doing to give you some stuff. I don't want to take what it is that the pair of us are doing for granted. We are not taking your presence here for granted. As I said before, on Wednesday when I met up with you, I saw some deficiencies. I'm asking you to work on the handouts that I gave you. I'm going to also ask you to go to your EducaSoft and start working on your EducaSoft. Please, guys, please. Time is against us. I am not the only one that is complaining, If you hear as team leader, I just have to be there to support my team members. And when they're ranting and raving, I say, guys, remember that I'm also there. I have the integrated math students. So it is a rough situation. You saw me take out half an hour, about 45 minutes to an hour of Miss Bartley's time. She too was complaining. Why? Because Caribbean Studies on the 4th of May. So you have integrated maths the Monday, Caribbean Studies is going to be on the Wednesday rather. All right? So it's rough for all of us. I know it's also rough for you. Do me a favor. When we are done and we sign out, which is in another few, I'm going to ask that you try and relax. If you want to go on a little social media, just to thaw out your brain a little bit. You may need to just go wrap up and just take a little sleep, but you have to get up tonight to do some work. Some of you may say, sir, I better do the work now or it's not going to sleep until tomorrow morning. Fair enough. Do some work. Always try to relax. Either watch a half an hour comedy, relax, and see you tomorrow morning. As soon as I get the link, I'll send it over to you. Please, you have to put what it is that we're putting tonight to long-term memory. It's a whole lot of stuff. But if you practice on it, you'll get it. Kasana, proud of you that answer. Natty B, that prep room talk was a good one. Proud of you. Just do what it is that you can do for me. I beg of you, I depend on you. Mrs. Henningham is depending on you. Me depend on you. Your parents, the institution, please. Do what you need to do. Come tomorrow. We will meet again as if I can strategize how it is that we're going to cover some more stuff. All right? Bless your hearts. Thank you. Later.
Bye, sir.
Bye,
Yeah,
sir. Good night,
Sir.
everyone.
Bye, Miss.
Hi, Miss.
Hey, JV.
If people ever hear you.
And the two participants in the meeting.
Yes, the people that will record this, they're gonna put on YouTube.
Why are you still in at the meeting?
No, me, I left now.
Oh. Bye-bye. You don't come here?
No, why you talk this again?
Oh.
YouTube never gonna hear you talk.